A thin sheet of plastic rises like a ghostly bubble inside a factory, stretching upward, shimmering under harsh lights, and somehow becoming the garbage bag you pull from a box at home. It looks fragile enough to pop with a touch. Yet minutes later, the same material can hold kilos of waste without tearing. How does something so delicate turn into something so tough? The answer lies in a tightly controlled industrial process that transforms tiny plastic pellets into continuous film, then into precisely cut and sealed bags. Every step matters. A slight change in temperature, air pressure, or thickness can ruin an entire batch. It starts small, really small. Garbage bags begin as polyethylene pellets, each about the size of a grain of rice. These pellets are made from long chains of hydrocarbons derived from petroleum or natural gas. At room temperature, they are solid, dry, and easy to handle. Pour them into a container and they flow like sand. There are two main types used here. Low-density polyethylene, known as LDPE, creates softer, stretchier bags. High-density polyethylene, or HDPE, produces thinner but stronger material with a slightly crinkly feel. The choice depends on the intended use. A heavy-duty contractor bag leans toward LDPE blends. A lightweight kitchen liner often uses HDPE. Before anything is melted, manufacturers often mix in additives. Black garbage bags get their color from carbon black, which also adds UV resistance. Slip agents reduce friction, so bags don't stick together. Anti-block additives prevent layers from clinging too tightly. If recycled plastic is used, which is common, it is blended carefully to maintain consistent quality. Too much variation and the final film becomes unpredictable. All of this material is fed into a hopper, a large funnel that sits above the extrusion machine. Gravity does the first bit of work, pulling pellets down into the system. Inside the extruder, the real transformation begins. A long steel screw, sometimes over 2 meters in length, rotates inside a heated barrel. As the pellets move forward along the screw, they are gradually heated in zones. Temperatures typically rise from around 150 degrees Celsius near the feed zone to about 200 to 230 degrees Celsius near the end. Depending on the polyethylene blend, the pellets soften, then melt completely, turning into a thick, viscous fluid. It is not watery. Think more like honey under pressure. The screw does more than push material forward. Its shape compresses and mixes the plastic, ensuring a uniform melt. Any air trapped between pellets is squeezed out. Additives disperse evenly. By the time the material reaches the end of the barrel, it has become a smooth, bubble-free mass. Pressure builds here, often reaching several hundred bar. This pressure forces the molten plastic through a die, which is where the next critical step happens. The die is a circular metal tool with a narrow opening, carefully machined to control thickness. When the molten plastic exits, it forms a continuous tube. At this point, it is still hot and soft, almost like thick syrup shaped into a hollow cylinder. Then air is introduced into the center of this tube through a small opening. This is where the process earns its name, blown film extrusion. The air inflates the tube outward, expanding it like a balloon. The diameter can grow several times larger than the die itself. Operators carefully control the air pressure to achieve the desired width and thickness. Too much pressure and the film thins out dangerously. Too little and the tube stays narrow and uneven. At the same time, the plastic is being pulled upward by rollers positioned several meters above the die. This upward motion stretches the material further. The combination of upward pulling and outward inflation determines the final properties of the film. Why stretch it? Stretching aligns the polymer chains, which improves strength. It is a bit like pulling fibers in a rope, so they line up and hold better together. The result is a tall, translucent bubble of plastic, often several meters high, rising steadily in the center of the machine. The floating bubble cannot stay soft for long. If it did, gravity would distort it and ruin the film. So the next step is rapid cooling. A ring of air nozzles surround the base of the bubble, blowing cool air evenly across its surface. This brings the temperature down quickly, solidifying the plastic while it is still under tension. The exact cooling rate matters. Cool too fast and the material can become brittle. Too slow and it may sag or develop uneven thickness. As the bubble rises, it transitions from glossy and flexible to matte and firm. This is where the structure is locked in. The thickness at this stage can be as low as 10 to 50 microns, which is thinner than a human hair. The bubble continues upward until it reaches a collapsing frame. Here, guide boards gently press the tube flat, turning the cylinder into a double-layered sheet. Once flattened, the plastic film passes through a set of rollers. These rollers control tension and ensure the film remains smooth and wrinkle-free. Any inconsistency here shows up later as weak spots or visual defects. The flattened tube is then wound onto large rolls. Each roll can contain hundreds or even thousands of meters of continuous film. At this stage, it still has no individual bags. It is just a long, seamless sleeve of plastic. Quality checks often happen here. Sensors measure thickness across the width of the film. Even small variations, say a few microns, can indicate problems in the extrusion process. Operators adjust temperature, air pressure, or screw speed to correct issues in real time. The next phase transforms that continuous film into individual units. The rolls are loaded into bag-making machines, which unroll the film at high speed. The machine measures out precise lengths, often between 50 and 120 centimeters, depending on the bag size. A cutting mechanism slices the film at regular intervals, but it does not fully separate each piece yet, if the bags are meant to stay on a roll. Instead, it creates perforations, tiny cuts spaced evenly so the bag can be torn off cleanly later. Timing is everything here. The machine must synchronize movement, cutting and sealing in fractions of a second. A slight misalignment can produce uneven bags or weak seams. A garbage bag is useless without a sealed bottom. This is done using heat sealing bars. These bars press against the film with controlled heat and pressure, melting the plastic layers together at one edge. The temperature is carefully set, often between 130 and 180 degrees Celsius, depending on the material. Too cool and the seal is weak. Too hot and the plastic burns or deforms. The pressure and dwell time, how long the bars stay in contact, are just as important. The goal is to fuse the layers into a single continuous piece without thinning the material too much at the seam. Some machines also create special seals, like star seals at the bottom of the bag. These distribute stress more evenly and are common in higher quality garbage bags. Once cut and sealed, the bags are folded or rolled into their final form. For roll-type bags, the machine winds the perforated strip into a compact roll, often around a cardboard core. The tension must be just right. Too tight and the bags are hard to pull apart. Too loose and the roll becomes messy. For folded bags, the machine stacks them in neat piles, folding each one into a compact shape that fits into a box. Automation dominates the stage. Sensors count each bag. If a roll is supposed to contain 30 bags, the machine stops exactly at that number. Errors are rare but monitored closely. The final step is packaging. Rolls are wrapped in plastic film or placed into printed boxes. Labels are added, indicating the size, the thickness, and the intended use. At this point, the transformation is complete. What began as small pellets has become a product ready for everyday use. What stands out in this process is how continuous it is. The plastic never stops moving. From the moment pellets enter the extruder to the moment finished bags are cut and rolled, the material flows in a steady stream. It is also a balancing act. Temperature, pressure, airflow, and speed all interact. Change one variable, and the entire system responds. Skilled operators watch for subtle signs, a slight wobble in the bubble, a faint change in film clarity, and adjust accordingly. And then there is the paradox at the center of it all. A garbage bag feels simple, disposable, almost insignificant. Yet creating one requires precise engineering, controlled physics, and constant monitoring. That thin sheet you tear off a roll has already been stretched, cooled, measured, cut, and sealed with remarkable accuracy. It has been shaped by heat, air, and motion into something that performs a specific task reliably. What makes this process especially striking is its scale and speed. A single production line can run continuously for hours, sometimes days, producing thousands of bags every hour without pause. The bubble never stops rising, the rollers never stop turning, and the cutters never miss their rhythm. It is a system built for consistency, where even a fraction of a second matters, and all of it exists to produce something most people use for a few minutes before throwing away. That contrast between effort and outcome is what makes the process so fascinating.